Hey everyone, tonight we're diving into one of astronomy's most mind-bending puzzles. How do you figure out the age of something that's been burning for billions of years? How do astronomers look at a distant star and somehow determine whether it's a cosmic newborn or an ancient relic older than Earth itself? It sounds impossible, right? Like trying to guess someone's age when they've looked exactly the same for their entire life. But here's the thing. Stars do age. They just do it in ways that are completely alien to anything we experience on Earth. And astronomers have developed some absolutely brilliant methods to crack this cosmic code. So before we get started, take a moment to like this video if you're ready to have your mind blown by the ingenuity of modern astronomy. And let me know in the comments where you're watching from and what time it is for you. There's something magical about knowing we're all looking up at the same stars. Separated by time zones, but connected by curiosity. Now settle in, maybe dim the lights, and let's journey into the fascinating world of stellar archaeology. Because what we're about to explore isn't just about measuring time, it's about understanding the very heartbeat of the universe itself. Imagine you're a detective, but instead of solving crimes, you're trying to solve the mystery of cosmic time. Your suspects are stars, scattered across billions of light years, each one holding secrets about when they were born and how long they've been shining. But here's the catch. Most stars are terrible witnesses. They barely change at all during their lifetimes. A star like our Sun will look almost identical for billions of years, burning with the same brightness, maintaining the same temperature, keeping the same size. It's like trying to determine the age of a person who never grows older, never gets wrinkles, never changes their appearance in any meaningful way. This is the fundamental challenge that has puzzled astronomers for over a century. Unlike planets that show clear signs of geological aging or galaxies that evolve and change over cosmic time, individual stars maintain an almost supernatural consistency. They're cosmic constants in a universe of change. Our Sun, for instance, has been burning steadily for about 4.5 billion years, and to a casual observer, it would have looked virtually identical throughout that entire span. No wonder early astronomers thought stars were eternal, unchanging fixtures in the heavens. But stars do have secrets. They do age. They just do it in ways that require incredible scientific detective work to uncover. And the story of how astronomers cracked this code is one of the most elegant examples of human ingenuity applied to cosmic mysteries. It's a story that spans from the early 20th century observations that first revealed stellar evolution to the cutting-edge space missions that can now measure the tiniest vibrations in distant stars. The breakthrough came when astronomers realized they were thinking about the problem all wrong. Instead of trying to age individual stars in isolation, they needed to study stellar families. They needed to find groups of stars that were born together at the same time from the same cosmic nursery. These stellar siblings would all have the same age, but crucially, they would have different masses. And mass, it turns out, is everything when it comes to stellar aging. Picture this scenario. You have a group of candles all lit at exactly the same moment. Some candles are thick, some are thin, some are made of different wax compositions. The thin candles will burn out first, the thick ones will burn longer. But if you come back hours later and see which candles are still burning and which have gone out, you can work backwards to figure out exactly when they were all lit. This is essentially what astronomers do with star clusters. Star clusters are cosmic laboratories where dozens, hundreds, or even thousands of stars formed from the same giant cloud of gas and dust at virtually the same time. These stellar nurseries give us something invaluable, a controlled experiment written across the sky. Every star in the cluster started its life simultaneously, but their different masses mean they age at dramatically different rates. The most massive stars burn bright and die young, sometimes lasting only a few million years. Medium-mass stars like our Sun can burn for billions of years. The smallest red dwarf stars are so efficient that they could theoretically burn for trillions of years, longer than the current age of the universe. This relationship between mass and stellar lifetime became the foundation for the most reliable method of determining stellar ages. It's called the main sequence turnoff method, and it's based on one of the most important diagrams in all of astronomy, the Hertzsprung-Russell diagram. This remarkable tool, developed independently by two astronomers in the early 1900s, plots stellar temperature against luminosity, creating a cosmic fingerprint that reveals exactly where a star sits in its evolutionary journey. When astronomers plot the stars in a young cluster on this diagram, they see a clear pattern. Most of the stars line up along what's called the main sequence, a diagonal band that represents stars in the prime of their lives, steadily fusing hydrogen in their cores. But as a cluster ages, something dramatic happens. The most massive, brightest stars begin to exhaust their nuclear fuel and evolve off the main sequence, swelling into red giants or exploding as supernovae. The beauty of this system is mathematical precision. By identifying exactly which type of star is just now leaving the main sequence, astronomers can determine the cluster's age with remarkable accuracy. If the turnoff point is at very massive blue stars, the cluster is young, maybe only a few million years old. If the turnoff has progressed down to stars like our Sun, the cluster is several billion years old. If only the smallest, faintest red stars remain on the main sequence, you're looking at an ancient cluster that's been burning for over 10 billion years. This method has revolutionized our understanding of cosmic timescales. Globular clusters, those spectacular spherical collections of hundreds of thousands of ancient stars, have turn-off points so far down the main sequence that we can date them to be among the oldest objects in our galaxy. Some globular clusters formed when the Milky Way was still taking shape, making them cosmic time capsules that preserve information about the very early universe. But what about individual stars that don't belong to clusters? What about field stars like our Sun that wander the galaxy alone without stellar siblings to provide age context? For decades, this seemed like an impossible problem. How do you age a star that shows no obvious signs of getting older? The answer came from an unexpected source: rotation. It turns out that stars are like cosmic spinning tops that gradually slow down over time. Young stars spin fast, old stars spin slowly. This happens because of a process called magnetic braking, where interactions between a star's magnetic field and its stellar wind gradually rob it of rotational energy. It's like an ice skater extending their arms to slow their spin, except the process takes billions of years. This discovery opened up an entirely new field called gyrochronology, essentially using stellar rotation as a cosmic clock. The relationship is surprisingly precise. Once astronomers calibrated this stellar speedometer using stars in clusters of known ages, they could measure the rotation rate of any individual star and calculate its age. Young stars might complete a rotation in just a few days, while ancient stars could take weeks to turn once on their axis. Measuring stellar rotation requires some clever detective work. Astronomers look for the subtle dimming and brightening caused by star spots, the stellar equivalent of sunspots. As these dark patches rotate in and out of view, they cause tiny but measurable changes in the star's brightness. By timing these variations, astronomers can determine exactly how fast the star is spinning. Space missions like Kepler have measured rotation periods for hundreds of thousands of stars, creating an unprecedented database of stellar ages across our galaxy. But the story gets even more sophisticated. Modern astronomy has developed techniques so advanced they seem almost magical. Asteroseismology, for instance, allows astronomers to listen to the vibrations of distant stars. Just as seismologists study earthquakes to understand Earth's interior, stellar seismologists analyze the tiny pulsations that travel through stellar interiors. These stellar heartbeats change subtly as stars age, providing another independent method for cosmic age determination. Even more remarkably, astronomers have learned to perform radioactive dating on stars themselves. By detecting incredibly faint traces of radioactive elements like uranium and thorium in stellar atmospheres, they can measure how much these elements have decayed since the star formed. It's like carbon dating, but for objects billions of light years away. Only a handful of stars have been analyzed this way, requiring the most advanced telescopes and spectroscopic techniques available to astronomy. Each of these methods tells part of the story, but none of them work perfectly for every type of star. Young, hot stars are best aged using cluster turn-off methods. Middle-aged stars like our Sun can be dated through rotation or astrosismology. Ancient, metal-poor stars might require nucleocosmochronology. The art of stellar age determination lies in knowing which technique to apply and how to combine multiple methods to build a complete picture. What emerges from this cosmic archaeology is a timeline of stellar birth and death that spans the entire history of the universe. We can identify stars that formed when the cosmos was young and metal-poor, containing only hydrogen and helium from the Big Bang. We can trace the chemical enrichment of our galaxy as successive generations of stars lived, died, and seeded space with heavier elements. We can even predict the future, calculating when our Sun will exhaust its fuel and begin its transformation into a red giant, eventually ending its life as a white dwarf. The precision of modern stellar age measurements continues to improve with each new space mission and theoretical advancement. What started as rough estimates based on crude observations has evolved into a sophisticated science capable of dating stars to within a few % of their actual ages. These measurements don't just satisfy scientific curiosity, they're essential for understanding galaxy formation, planet formation, and even the conditions necessary for life. The implications of stellar age measurements extend far beyond academic curiosity. When astronomers determine that our Sun is roughly 4.6 billion years old, they're not just measuring one star, they're establishing a cosmic timeline that connects to everything from the formation of our solar system to the evolution of life on Earth. Every meteorite that falls to our planet, every rock sample brought back from the Moon, every ancient zircon crystal found in Earth's oldest formations tells the same story. Our corner of the universe began taking shape when the cosmos was already 2/3 of its current age. But here's where stellar age determination becomes truly mind-bending. Different methods sometimes give different answers, and reconciling these discrepancies has led to some of the most profound discoveries in modern astrophysics. When astronomers first applied nucleocosmochronology to extremely metal-poor stars, the results were shocking. Some of these ancient stellar relics appeared to be older than the universe itself, a cosmic impossibility that sent theorists scrambling. The resolution came through more sophisticated modeling of galactic chemical evolution and better measurements of the cosmic expansion rate. These apparent paradoxes weren't failures of stellar age determination. They were clues to deeper truths about cosmic history, the nature of dark matter, and the complex processes that govern stellar birth and death. Every discrepancy between methods becomes a puzzle piece that helps astronomers refine their understanding of how stars actually work. Consider the challenge facing astronomers studying the oldest stars in our galaxy. These ancient objects formed when the Milky Way was still a chaotic collection of smaller galaxies merging together. They contain almost no heavy elements, just the primordial hydrogen and helium left over from the Big Bang, with tiny traces of lithium. Dating these stars requires extraordinary precision because they represent our only direct connection to the cosmic dark ages. The era before the first stars had time to forge and distribute the elements essential for planets and life. The star HE 1523-0901 stands as a perfect example of this cosmic archaeology in action. This unassuming point of light in the constellation Libra doesn't look like much through a telescope. It's faint, reddish, easily overlooked among the thousands of other stars in its field of view. But spectroscopic analysis reveals it to be a cosmic time machine, a relic from when our galaxy was young and the universe was a very different place. When astronomers detected traces of radioactive thorium and uranium in this star's atmosphere, they were essentially performing forensic analysis on cosmic history. The ratios of these elements, measured with incredible precision using the world's most advanced telescopes, told a story of radioactive decay spanning more than 13 billion years. This single star had been burning since before our solar system existed, since before most of the heavy elements in your body had been manufactured in stellar cores. The technical challenges involved in such measurements push the boundaries of what's possible with current technology. Detecting uranium in a distant star requires identifying spectral lines so faint that they're barely distinguishable from instrumental noise. The observations demand perfect atmospheric conditions, months of telescope time, and data processing techniques that extract meaningful signals from measurements at the very edge of detectability. Yet these extreme efforts reveal cosmic truths that would be impossible to discover any other way. When astronomers compare the ages of the oldest stars with the age of the universe itself, they're testing our most fundamental theories about cosmic evolution. The fact that we don't find any stars significantly older than 13.8 billion years provides independent confirmation of the Big Bang timeline. The universe hasn't existed long enough for older stars to form and survive. Meanwhile, gyrochronology continues to revolutionize our understanding of stellar populations throughout the galaxy. The Nancy Grace Roman Space Telescope, set to launch in the coming years, will measure rotation periods for millions of stars simultaneously, creating an unprecedented census of stellar ages across vast regions of space. This data will reveal patterns of star formation stretching back billions of years, showing how our galaxy has evolved from a chaotic early structure into the elegant spiral we see today. The relationship between stellar rotation and age also connects to one of astronomy's most exciting frontiers: the search for potentially habitable exoplanets. Young stars tend to be magnetically active, producing powerful flares and energetic particle radiation that could strip away planetary atmospheres. Older stars are generally more stable, providing the calm, steady energy output that might allow life to evolve and thrive. By measuring stellar ages, astronomers can identify the most promising targets for detailed studies of planetary habitability. This connection between stellar age and the potential for life represents one of the most profound applications of stellar chronometry. When the James Webb Space Telescope analyzes the atmospheres of distant exoplanets, searching for biosignatures or signs of technological civilizations, the age of the host star provides crucial context. A planet orbiting a billion-year-old star has had much less time for biological evolution than one orbiting a star that's been burning steadily for 8 billion years. Asteroseismology has emerged as perhaps the most precise technique for aging individual stars, capable of determining stellar ages to within a few percent. The method works by analyzing the acoustic waves that continuously bounce around inside stellar interiors, much like studying the resonant frequencies of a musical instrument. These stellar oscillations are incredibly subtle, causing brightness variations of just a few parts per million, but space-based telescopes can measure them with extraordinary precision. The frequency patterns revealed by asteroseismology contain a wealth of information about stellar structure and evolution. Young stars have different internal density profiles than old stars, and these differences manifest as subtle shifts in oscillation frequencies. By comparing observed frequencies with detailed theoretical models, astronomers can determine not just age, but also mass, radius, and internal composition with remarkable accuracy. The Sun serves as the perfect laboratory for developing and testing astroseismic techniques. Solar oscillations have been studied for decades, creating a detailed understanding of how acoustic waves propagate through our star's interior. This solar template allows astronomers to interpret similar oscillations in distant stars, essentially using the Sun as a Rosetta Stone for stellar seismology. But astroseismology reveals surprises that challenge our understanding of stellar evolution. Some stars show oscillation patterns that don't match theoretical predictions, suggesting that stellar interiors are more complex than models assume. These anomalies often point to phenomena like magnetic fields, rotation, or chemical mixing processes that aren't fully accounted for in standard stellar evolution theory. The quest to understand stellar aging has also revealed fundamental connections between stars and the cosmic environment. Stars don't evolve in isolation. They're influenced by their galactic neighborhoods, by encounters with interstellar clouds, by gravitational interactions with companion stars. Ancient stars in the galactic halo show different chemical compositions than younger stars in the galactic disk, reflecting the changing conditions under which they formed. These environmental effects complicate age determinations, but also provide valuable insights into galactic evolution. The oldest stars in our galaxy are scattered throughout a roughly spherical halo, suggesting they formed before the Milky Way had settled into its current disk structure. Younger stars are concentrated in the spiral arms, where ongoing star formation continues to create new stellar generations. The precision required for modern stellar age measurements has driven remarkable advances in both observational techniques and theoretical modeling. Spectrographs capable of measuring wavelengths to 1 part in a million. Space telescopes that can detect brightness changes smaller than the dimming caused by a fly passing in front of a searchlight. Computer simulations that model the complex physics of stellar interiors with unprecedented detail. Each improvement in measurement precision reveals new subtleties in stellar evolution. Stars that once seemed identical are found to have slightly different ages, reflecting small variations in their formation conditions or evolutionary paths. The galaxy begins to look less like a collection of similar objects and more like a complex ecosystem where every star has its own unique history and destiny. These advances in stellar chronometry have unveiled patterns that would have been unimaginable just a few decades ago. When astronomers map the ages of thousands of stars across different regions of our galaxy, they're essentially creating a time-lapse movie of cosmic evolution. The oldest stars cluster in the central bulge and outer halo, relics from the Milky Way's chaotic youth when smaller galaxies were still merging together. The youngest stars trace out the elegant spiral arms where gas clouds continue to collapse and ignite new stellar fires. But the real magic happens when these techniques are combined. A single star might be analyzed using rotation measurements, asteroseismology, and chemical composition studies simultaneously. When all three methods agree, astronomers can be confident in their age determination. When they disagree, it often signals something fascinating is happening that standard models don't predict. Take the case of subgiant stars, those objects caught in the brief transition between main sequence burning and red giant expansion. These stars are particularly valuable for age studies because they're undergoing rapid changes that make their evolutionary state obvious. By combining astroseismic measurements with precise photometry, astronomers can determine the ages of subgiants to within just a few %, creating cosmic chronometers of extraordinary precision. The study of stellar ages has also revealed one of the most surprising discoveries in modern astronomy. Some stars appear to be older than they should be, given their chemical composition. These objects, called blue stragglers, seem to have found a way to cheat stellar evolution, appearing younger and more massive than their cluster companions. The mystery was solved when astronomers realized these weren't single stars at all, but the products of stellar mergers or mass transfer between close binary companions. Binary star systems, where two stars orbit around their common center of mass, present both challenges and opportunities for age determination. The gravitational interactions between stellar companions can alter rotation rates, strip away outer layers, or trigger episodes of enhanced nuclear burning. Dating binary stars requires sophisticated modeling of these complex interactions, but the effort reveals insights into stellar evolution that would be impossible to gain from single stars alone. The precision of modern age measurements has become so refined that astronomers can now detect the subtle effects of stellar magnetic fields on evolutionary timescales. Stars with stronger magnetic fields evolve slightly differently than their non-magnetic counterparts, differences that show up as tiny shifts in oscillation frequencies or rotation periods. These magnetic signatures provide yet another tool for understanding stellar chronology and the complex physics governing stellar interiors. Perhaps the most mind-bending application of stellar age determination involves studying stars that are older than the disk of our galaxy. These ancient objects, sometimes called fossil stars, formed during the Milky Way's earliest epochs, when the galactic environment was completely different from today. They contain almost no elements heavier than hydrogen and helium, making them living laboratories for studying the universe as it existed more than 12 billion years ago. The search for these cosmic fossils requires patience and sophisticated analysis. Astronomers must survey hundreds of thousands of stars to find the rare specimens with the right combination of age indicators and chemical signatures. When such objects are discovered, they become the subject of intensive follow-up observations using the world's most advanced telescopes and instruments. One particularly remarkable example is the star designated SJ 0313-6708, an object so ancient and metal poor that it may have formed from gas clouds enriched by just a single previous generation of stars. This stellar relic provides a direct connection to the epoch of first star formation, when the universe was emerging from its dark ages and beginning to forge the first heavy elements in stellar cores. The implications extend far beyond academic curiosity. Understanding when the first stars formed and how they evolved helps astronomers model the rionization of the universe, the process by which stellar radiation gradually cleared the cosmic fog that pervaded the early cosmos. These ancient stars are witnesses to one of the most important phase transitions in cosmic history. Modern surveys are now discovering that stellar ages show unexpected correlations with galactic structure. Stars in different spiral arms often have subtly different age distributions, reflecting the complex dynamics of galactic rotation and star formation. The Perseus arm contains a higher fraction of young stars than the Sagittarius arm, suggesting that spiral density waves trigger star formation in predictable patterns as they sweep around the galaxy. These galactic scale patterns emerge only when astronomers can determine ages for thousands of stars simultaneously. Space missions like Gaia, which has measured precise positions and motions for over 1 billion stars, combined with ground-based spectroscopic surveys that determine stellar ages, are creating the first comprehensive maps of how our galaxy has evolved over cosmic time. The future of stellar age determination lies in pushing these techniques to even greater precision and applying them to ever larger samples of stars, Machine learning algorithms are being trained to recognize age indicators in stellar spectra automatically, allowing astronomers to process data from millions of stars simultaneously. These artificial intelligence systems can identify subtle patterns that human analysts might miss, revealing new correlations between stellar age and observable properties. Upcoming space missions will extend these capabilities even further. The Nancy Grace Roman Space Telescope will measure rotation periods for stars throughout the galaxy, while the extremely large telescope will enable astroseismic studies of individual stars in nearby galaxies. These observations will test whether stellar evolution proceeds the same way in different galactic environments and at different cosmic epochs. The quest to understand stellar aging has also revealed fundamental connections to some of the biggest questions in cosmology. When astronomers measure the ages of the oldest stars and compare them to the age of the universe derived from cosmic microwave background observations, they're testing the consistency of our entire cosmological model. The fact that no stars appear to be older than the Big Bang provides powerful confirmation of our understanding of cosmic chronology. Yet mysteries remain. Some globular clusters show small but significant age spreads, suggesting that star formation in these ancient systems was more complex than previously thought. Certain metal-poor stars display abundance patterns that don't match theoretical predictions for early stellar nucleosynthesis. These anomalies drive continued refinement of stellar evolution models and nucleosynthesis theory. The relationship between stellar age and habitability continues to evolve as exoplanet discoveries reveal the diversity of planetary systems. Young stars produce high-energy radiation that can strip planetary atmospheres, but they also heat their planets more uniformly through tidal interactions. Old stars provide stable energy output, but may have depleted the volatile elements necessary for planet formation. Finding the optimal stellar age for habitability remains an active area of research. Stellar chronometry has also revealed the dynamic nature of our own solar neighborhood. The stars visible in Earth's night sky span an enormous range of ages, from relatively recent arrivals like Vega, which formed just a few 100 million years ago, to ancient wanderers like Captain's star, which has been orbiting the galaxy for over 11 billion years. Each of these stellar neighbors carries information about different epochs in galactic history. The Sun itself serves as a benchmark for middle-aged stellar evolution. At 4.6 billion years old, our star has consumed roughly half of the hydrogen fuel in its core and is slowly brightening as nuclear fusion rates increase. Detailed models predict that this gradual evolution will eventually make Earth uninhabitable, but not for another billion years or more. Understanding solar aging provides crucial context for the long-term future of our planet. Advanced spectroscopic techniques continue to push the boundaries of what's possible in stellar age determination. Astronomers can now detect isotopic ratios in stellar atmospheres, revealing information about the nuclear processes that forged different elements. The ratio of oxygen-16 to oxygen-18, for instance, depends on the stellar generation that produced these isotopes, providing another clock for cosmic chronology. The precision of these measurements requires extraordinary attention to detail. Atmospheric turbulence, instrumental effects, and even the motion of Earth around the Sun can introduce systematic errors that must be carefully calibrated away. The most accurate stellar age measurements involve years of observations with multiple independent techniques, cross-checking results until astronomers are confident in their conclusions. Perhaps most remarkably, stellar age determination has become precise enough to detect the effects of galactic dynamics on individual stars. Ancient stars show kinematic signatures of the galaxy's violent past, when smaller satellite galaxies were torn apart by tidal forces and their stars scattered into the Milky Way's halo. By combining age measurements with precise astrometry from space missions, astronomers can literally watch the archaeological remains of galactic cannibalism playing out in stellar motions. These discoveries transform our understanding of how galaxies grow and evolve. Rather than smooth, gradual processes, galactic evolution appears to be punctuated by dramatic merger events that leave lasting signatures in stellar populations. The Milky Way bears the scars of these ancient collisions in the form of stellar streams, disrupted clusters, and chemical abundance patterns that tell stories of cosmic violence and rebirth. The techniques pioneered for stellar age determination are now being applied to other astronomical objects. White dwarf stars, the cooling remnants of sun-like objects, can be dated through their temperatures and cooling rates. Neutron stars show age-related changes in their rotation and magnetic field evolution. Even brown dwarfs, the failed stars that never achieved sustained nuclear fusion, gradually cool and fade in ways that reveal their formation epochs. Each new application extends our ability to piece together cosmic history from the fossil record written in starlight. The universe becomes less mysterious and more comprehensible as astronomers develop ever more sophisticated techniques for reading the temporal signatures hidden in astronomical observations. What started as a simple question about stellar ages has evolved into a comprehensive framework for understanding cosmic evolution across 13.8 billion years of history. The story of stellar chronometry illustrates one of the most beautiful aspects of modern science. Complex, seemingly impossible problems yield to patient observation, theoretical insight, and technological innovation. What once appeared to be eternal, unchanging points of light have revealed themselves to be dynamic, evolving objects that carry information about the deepest workings of the cosmos. Through the ingenuity of stellar age determination, astronomers have learned to read time itself in the language of starlight, light. The marriage between stellar age determination and exoplanet science has created one of astronomy's most exciting frontiers. When the Kepler Space Telescope discovered thousands of planetary systems orbiting distant stars, it wasn't just finding new worlds. It was uncovering a cosmic laboratory where stellar age becomes the crucial variable in understanding planetary evolution. A rocky planet orbiting a young, magnetically active star faces a completely different environment than one circling an ancient, stable stellar host. Consider the TRAPPIST-1 system, where 7 Earth-sized planets orbit an ultra-cool red dwarf star. Age determination suggests this system could be anywhere from a few 100 million to several billion years old, a range that dramatically affects the potential for habitability. Young red dwarfs unleash powerful stellar flares that could strip away planetary atmospheres in geological eye blinks. Ancient ones settle into the kind of stable, long-term energy output that might allow complex chemistry to evolve over cosmic timescales. The challenge of dating red dwarf stars illustrates the ongoing evolution of stellar chronometry. These dim, long-lived objects burn their nuclear fuel so slowly that they barely change over billions of years. Traditional main sequence turn-off methods fail because red dwarfs can remain virtually unchanged for timescales longer than the current age of the universe. Gyrochronology offers some hope, but measuring rotation periods for such faint stars pushes current technology to its limits. Enter the next generation of space-based observatories. The James Webb Space Telescope, with its unprecedented infrared sensitivity, can detect the subtle spectroscopic signatures that reveal stellar ages even in these challenging objects. By analyzing the ratios of different carbon and oxygen isotopes in stellar atmospheres, Webb can peer back through billions of years of galactic chemical evolution, using the changing composition of interstellar gas as a cosmic clock. The precision required for such measurements defies comprehension. Astronomers must distinguish between spectral lines that differ by fractions of an angstrom, detecting abundance variations of just a few percent in starlight that has traveled for decades or centuries to reach our telescopes. The fact that this is possible at all represents a triumph of human ingenuity and technological sophistication, but stellar age determination reveals patterns that extend far beyond individual objects. When astronomers plot the ages of thousands of stars against their positions in the galaxy, a remarkable picture emerges. The Milky Way shows clear age gradients, with the oldest stars concentrated in the central bulge and outer halo, while younger populations trace the spiral arms where active star formation continues today. These patterns tell the story of galactic assembly over cosmic time. The earliest stars formed in small, chaotic proto-galactic fragments that gradually merged and settled into the rotating disk structure we see today. Each generation of stellar death and rebirth enriched the interstellar medium with heavier elements, changing the conditions under which subsequent stars could form. The chemical evolution of our galaxy becomes a temporal roadmap written in stellar abundances. Stars that formed 12 billion years ago contain almost pure hydrogen and helium, the primordial elements forged in the Big Bang. Younger stars show progressively higher concentrations of carbon, oxygen, silicon, iron, and other heavy elements manufactured in previous stellar generations. By measuring both age and chemical composition, astronomers can trace the gradual transformation of our galaxy from a metal-poor collection of gas clouds into the chemically complex environment that eventually gave birth to planets and life. This cosmic archaeology has revealed surprising details about the Milky Way's violent past. Around 10 billion years ago, our galaxy experienced a major merger event when a smaller satellite galaxy, now called Gaia Enceladus, was torn apart by tidal forces and its stars scattered throughout the galactic halo. The stellar refugees from this ancient collision can still be identified today through their unusual orbital motions and distinctive chemical signatures. These discoveries emerged only when astronomers combined precise age measurements with the exquisite astrometric data from the Gaia space mission. By tracking the three-dimensional motions of hundreds of millions of stars, Gaia revealed kinematic patterns that had been hidden for billions of years. Ancient stellar streams, the gravitational echoes of long-destroyed star clusters, snake across the sky like fossil rivers preserved in the galactic tide. The technical challenges involved in such studies push observational astronomy to its absolute limits. Measuring the motion of a star across the sky requires detecting positional changes smaller than the width of a human hair seen from 1,000 miles away. Determining stellar ages through asteroseismology involves analyzing brightness variations that amount to just a few parts per million. Chemical abundance measurements demand spectrographs stable enough to detect wavelength shifts equivalent to the Doppler effect from a person walking slowly across a room. Yet these extreme measurements reveal cosmic truths that would be impossible to discover any other way. The age structure of stellar populations provides our most direct window into the formation and evolution of galaxies themselves. When astronomers study similar patterns in nearby galaxies, they're essentially watching the Milky Way's biography played out in countless cosmic theaters across the universe. The relationship between stellar age and galactic dynamics continues to yield surprises. Recent studies have discovered that stars in the outer regions of our galaxy's disk show evidence of a dramatic rejuvenation event that occurred roughly 2 to 3 billion years ago. Something, perhaps the gravitational influence of a passing dwarf galaxy or the internal dynamics of spiral density waves, triggered a burst of star formation that left lasting signatures in the current stellar population. These patterns emerge only when astronomers can determine ages for statistically significant samples of stars across large regions of space. Ground-based spectroscopic surveys like Apogee and Gaia ESO have measured chemical abundances for hundreds of thousands of stars. while space missions provide the photometric precision necessary for asteroseismic age determination. The combination creates an unprecedented database of stellar chronometry spanning the entire galaxy. Machine learning algorithms have become essential tools for processing this avalanche of data. Neural networks trained on stellar spectra can automatically identify age-sensitive features that human analysts might overlook. These artificial intelligence systems can process observations of millions of stars simultaneously, revealing subtle correlations between age, chemistry, and galactic position that would take human researchers decades to discover through traditional methods. The applications extend beyond pure astronomy. Stellar age determination has become crucial for astrobiology, helping identify the most promising targets for searches for extraterrestrial life. Stars need time to settle into stable, long-term energy output before complex planetary atmospheres can evolve. Too young, and stellar activity strips away any atmosphere a planet might develop. Too old, and the star may have already begun its evolution toward becoming a red giant, rendering any previously habitable worlds uninhabitable. The Goldilocks zone for stellar age appears to be roughly 1 to 8 billion years, old enough for stability, but young enough to avoid late-stage evolution. Our Sun, at 4.6 billion years old, sits comfortably in this range, providing a stable energy source that has allowed Earth's atmosphere and biosphere to evolve over geological timescales. Understanding stellar chronometry thus becomes essential for identifying potentially habitable exoplanets and planning future missions to study their atmospheres. But stellar age determination also reveals the finite nature of stellar evolution and the ultimate fate awaiting all stars. Even the longest-lived red dwarfs will eventually exhaust their nuclear fuel, though not for trillions of years. More massive stars like our Sun will evolve into red giants in just a few billion years, eventually ending their lives as slowly cooling white dwarf stars. The most massive stars burn so brightly that they exhaust their fuel in just millions of years before exploding as supernovae. These evolutionary timescales provide cosmic perspective on the temporary nature of stellar energy sources. The universe is currently in its stellar epoch, when nuclear fusion provides the dominant source of energy and light. But this phase won't last forever. In the far future, as star formation slows and existing stars burn out, the cosmos will gradually fade into a cold, dark state dominated by slowly cooling stellar remnants. Stellar chronometry allows astronomers to predict this cosmic future with remarkable precision. By measuring the current ages and masses of stars throughout the galaxy, they can model the decline of stellar populations over the next 100 billion years. The predictions paint a picture of gradual dimming as massive stars exhaust their fuel and explode, leaving behind increasingly dominant populations of long-lived red dwarfs. These distant futures seem almost incomprehensibly remote, but they highlight the precious nature of our current cosmic moment. We live during the relatively brief epoch when stars burn brightly, when heavy elements are abundant enough to form rocky planets, when conditions exist for the complex chemistry that enables life. Stellar age determination reminds us that this golden age of cosmic evolution won't last forever. The quest to understand stellar aging has also revealed fundamental connections to particle physics and our understanding of matter itself. The nuclear fusion processes that power stellar cores depend on the fundamental constants of nature, the strengths of electromagnetic and nuclear forces that determine how protons combine to form heavier elements. Precise measurements of stellar evolution provide tests of these fundamental constants over cosmic time. Some theories suggest that the fundamental constants might have evolved slowly over the history of the universe. If true, this evolution would leave subtle signatures in stellar nucleosynthesis and evolution that could be detected through sufficiently precise age determinations. While no such variations have been confirmed, the possibility keeps theorists interested in pushing stellar chronometry to ever greater precision. The development of stellar age determination techniques has also driven remarkable advances in computational astrophysics. Modern stellar evolution models require sophisticated three-dimensional simulations that account for magnetic fields, rotation, convection, and mass loss. These calculations demand some of the most powerful supercomputers available to science, generating theoretical predictions that can be compared directly with observational data. The interplay between theory and observation has led to continuous refinement of our understanding of stellar physics. Each new measurement of stellar ages and properties provides a test of theoretical models, often revealing discrepancies that point toward previously unknown physical processes. The discovery that stellar rotation affects evolution more strongly than initially expected emerged from careful comparisons between predicted and observed age indicators. These theoretical advances have practical implications for stellar age determination itself. As models become more sophisticated, they provide more accurate templates for interpreting observational data. Asteroseismic age determinations, for instance, rely heavily on detailed theoretical calculations of how sound waves propagate through stellar interiors. Improvements in the underlying physics translate directly into more precise age measurements. The precision of modern stellar chronometry has reached the point where astronomers can detect the subtle effects of planetary companions on stellar evolution. Massive planets orbiting close to their host stars can cause slight changes in stellar rotation and magnetic field evolution. While these effects are tiny, they're becoming measurable with current techniques, opening up new possibilities for studying star-planet interactions over cosmic timescales. Binary star systems present both challenges and opportunities for age determination. The gravitational interactions between stellar companions can significantly alter evolutionary timescales, making single-star models inadequate for dating such systems. However, binary stars also provide unique laboratories for testing stellar physics, since both components formed at the same time but may have different masses and evolutionary histories. Eclipsing binary systems offer particular advantages for stellar chronometry. When one star passes in front of another as seen from Earth, precise photometry can determine stellar radii and masses with extraordinary accuracy. Combined with spectroscopic measurements of temperature and chemical composition, these observations constrain stellar ages more precisely than is possible for single stars. The study of stellar ages has also revealed the complex relationship between stellar evolution and galactic chemical evolution. Each generation of stars changes the composition of the interstellar medium through stellar winds and supernova explosions. These compositional changes affect the properties of subsequently forming stars, creating feedback loops that influence galactic evolution over cosmic time. Understanding these feedback processes requires combining stellar chronometry with models of galactic chemical evolution. By measuring ages and abundances for large samples of stars, astronomers can trace the history of element production and mixing throughout the galaxy. The results reveal that chemical evolution proceeds differently in various galactic environments, with the central bulge evolving more rapidly than the outer disk regions. The implications extend to our understanding of planet formation and habitability. Rocky planets require significant concentrations of heavy elements like silicon, iron, and magnesium. These elements become available only after several generations of stellar evolution have enriched the interstellar medium. By measuring when different galactic regions reach the metallicity threshold for planet formation, astronomers can identify the epochs when habitable worlds first became possible. The search for the oldest stars in our galaxy continues to push the boundaries of stellar chronometry. These ancient objects, sometimes called population 3 remnants, formed from the primordial hydrogen and helium left over from the Big Bang. Finding and studying such stars would provide direct observational contact with the universe's first stellar generation, currently accessible only through theoretical models. The technical challenges are enormous. If any population 3 stars survive today, they would be extremely rare and difficult to identify among the billions of stars in our galaxy. They would also be very faint, having exhausted much of their nuclear fuel over cosmic timescales. Detecting and studying such objects requires the most sensitive telescopes and sophisticated analysis techniques available to modern astronomy. Yet, the potential rewards justify the effort. A confirmed population 3 star would provide unprecedented insights into the earliest phases of cosmic evolution, when the universe was emerging from its dark ages and beginning to forge the first heavy elements. Such discoveries could revolutionize our understanding of how the first galaxies formed and evolved. The future of stellar age determination lies in combining multiple techniques with ever-improving precision. Space missions like Plato, scheduled for launch in the coming decade, will conduct astroseismic surveys of unprecedented scope and sensitivity. Ground-based, extremely large telescopes will enable spectroscopic studies of individual stars in nearby galaxies. Machine learning algorithms will extract age information from subtle patterns in stellar data that human researchers might never notice. These advances promise to transform our understanding of cosmic evolution. By measuring precise ages for millions of stars across different galactic environments, astronomers will create the first comprehensive timeline of how galaxies form, evolve, and interact over cosmic history. The story written in starlight will become as detailed and precise as the geological record preserved in Earth's rocks. The quest to understand stellar aging represents one of humanity's most ambitious intellectual achievements. From the initial recognition that stars evolve and age to the development of techniques precise enough to date individual objects to within a few percent, the field exemplifies the power of scientific methodology applied to cosmic mysteries. Each breakthrough in stellar chronometry has opened new windows into the universe's past, present, and future. The techniques that allow us to age stars also reveal the conditions necessary for planet formation, the timescales for biological evolution, and the ultimate fate awaiting all stellar systems. In learning to read time itself in the language of starlight, astronomers have unlocked one of the cosmos's most closely guarded secrets. Yet mysteries remain. The relationship between stellar age and magnetic field evolution continues to yield surprises. The role of stellar companions in affecting evolutionary timescales requires further investigation. The search for population 3 remnants and other exotic stellar populations drives continued innovation in observational techniques. Perhaps most importantly, stellar age determination connects us to our cosmic origins. Every element in our bodies heavier than hydrogen was forged in stellar cores and distributed through space by stellar winds and supernova explosions. The calcium in our bones, the iron in our blood, the oxygen we breathe, all bear the temporal signatures of stellar evolution stretching back billions of years. By learning to measure stellar ages, astronomers have given us the ability to trace our own cosmic ancestry through the generations of stars that lived and died before our solar system formed. We are literally made of star stuff, and stellar chronometry allows us to read the timestamps of our cosmic heritage written in the very atoms of our existence. The precision of these measurements continues to improve with each passing year. What began as rough estimates based on crude stellar models has evolved into a sophisticated science capable of dating stars with remarkable accuracy. Space missions provide photometric precision measured in parts per million. Spectrographs resolve wavelength differences smaller than the width of atomic nuclei. Computational models simulate stellar evolution with unprecedented detail and sophistication. These technical achievements serve a deeper purpose than mere scientific curiosity. Understanding stellar ages provides essential context for the search for extraterrestrial life, the study of galactic evolution, and our comprehension of cosmic history. Every measurement of stellar chronometry adds another piece to the vast puzzle of how the universe has evolved from its simple beginnings into the complex, chemically rich cosmos we observe today. The story of stellar age determination illustrates science at its most elegant and powerful. Through careful observation, theoretical insight, and technological innovation, astronomers have learned to extract temporal information from the faintest whispers of starlight. They have transformed the apparently eternal, unchanging stars into cosmic chronometers that reveal the deep history of the universe itself. In the end, stellar chronometry reminds us that even the seemingly permanent features of our cosmic environment are temporary. Stars are born, age, and die on timescales that dwarf human experience but are finite nonetheless. The light we see from distant stars carries information about when those stars formed, how they have evolved, and what fate awaits them in the cosmic future. Through the patient work of stellar astronomers, we have learned to read these temporal messages written in starlight across the electromagnetic spectrum. Each photon carries data about stellar age, composition, and evolutionary state. Each measurement adds to our understanding of how the cosmos has changed over its 13.8 billion year history. The techniques pioneered for stellar age determination continue to find new applications throughout astronomy. The same methods used to date individual stars now help astronomers understand galaxy formation, trace the chemical evolution of the universe, and search for potentially habitable exoplanets. What started as a quest to measure stellar ages has become a comprehensive framework for understanding cosmic evolution. A comprehensive framework for understanding cosmic evolution. The elegance of stellar chronometry becomes even more apparent when we consider how these ancient techniques are being revolutionized by artificial intelligence. Machine learning algorithms now scan through vast databases of stellar observations, identifying patterns that would take human astronomers lifetimes to recognize. These digital detectives can spot the subtle correlations between stellar brightness variations and age indicators across millions of stars simultaneously, revealing connections that were previously invisible to traditional analysis methods. What's truly remarkable is how these computational approaches are uncovering stellar populations that challenge our basic assumptions about galactic evolution. Some stars appear to have formed in environments so different from today's galaxy that they represent fossil evidence of cosmic conditions that no longer exist anywhere in the observable universe. These stellar time capsules preserve information about epochs when the Milky Way was a chaotic, turbulent system, still digesting smaller galaxies and struggling to establish its current, elegant spiral structure. The precision required for these discoveries pushes the boundaries of what's physically possible with current technology. Consider the challenge of measuring stellar oscillations in distant red giant stars. These ancient objects pulsate with periods measured in hours or days, but the brightness variations they produce are incredibly subtle. Detecting them requires space telescopes capable of measuring changes in starlight equivalent to distinguishing between a 100-watt bulb and a 99-watt bulb from a distance of several thousand miles. Yet these extreme measurements yield insights that transform our understanding of cosmic history. When astronomers detect asteroseismic signatures in a red giant star located in the galactic halo, they're not just measuring one object's age. They're probing the conditions that existed when our galaxy was young, when star formation proceeded under completely different circumstances than we observe today. The chemical fingerprints preserved in these ancient stars tell stories of cosmic violence and renewal that span billions of years. Some show abundance patterns, suggesting they formed from gas clouds enriched by just a handful of earlier supernovae. Others display chemical signatures, indicating they were born in small dwarf galaxies that were later consumed by the growing Milky Way. Each stellar spectrum becomes a page in the autobiography of our cosmic neighborhood. But perhaps the most mind-bending aspect of modern stellar chronometry is its ability to reveal the future as clearly as the past. By measuring the current ages and evolutionary states of stars throughout the galaxy, astronomers can predict with remarkable precision what our cosmic neighborhood will look like billions of years from now. The models paint a picture of gradual change punctuated by dramatic events as individual stars exhaust their nuclear fuel and begin their final evolutionary phases. Our own sun serves as a perfect example of this predictive power. Detailed astroseismic studies have revealed that our star is slowly brightening as nuclear fusion rates in its core gradually increase. This evolution proceeds so slowly that it's imperceptible on human timescales, but over geological time, it will have profound consequences for Earth's climate and habitability. The precision of stellar age measurements allows astronomers to calculate exactly when our planet will become uninhabitable due to this solar evolution. The timeline is both reassuring and sobering. Earth has roughly another billion years before increasing solar luminosity begins to seriously disrupt our planet's climate systems. That's enough time for evolution to produce entirely new forms of life, for continents to drift into unrecognizable configurations, for mountain ranges to rise and erode away completely. Yet from a stellar perspective, it's just a brief moment in our sun's 10 billion year main sequence lifetime. These long-term predictions become even more fascinating when applied to the thousands of exoplanetary systems discovered by space missions like Kepler and TESS. Many of these distant worlds orbit stars that are either much younger or much older than our Sun, providing natural laboratories for studying how planetary systems evolve over cosmic time. Young systems show us what Earth might have been like billions of years ago, while ancient ones preview what might await our solar system in the far future. The relationship between stellar age and planetary habitability reveals surprising complexities that continue to reshape our understanding of where life might exist in the universe. Very young stars produce intense ultraviolet radiation and powerful stellar flares that can strip away planetary atmospheres before they have time to develop complex chemistry. But very old stars may have depleted the heavy elements necessary for rocky planet formation, or they may have already begun evolving toward red giant phases that would sterilize any previously habitable worlds. Finding the optimal stellar age for life requires balancing these competing factors, and the answer appears to depend on the specific characteristics of both the star and its planetary system. Some simulations suggest that red dwarf stars, despite their youth and activity, might actually provide more stable long-term environments for life than Sun-like stars. Their incredibly long main sequence lifetimes could allow biological evolution to proceed over timescales that dwarf the entire history of life on Earth. The search for potentially habitable exoplanets has driven remarkable advances in stellar characterization techniques. Astronomers now routinely measure stellar ages, masses, and compositions with precision that would have been unimaginable just decades ago. These detailed stellar censuses provide the essential context needed to evaluate whether distant worlds might harbor conditions suitable for life as we know it. But stellar chronometry also reveals the cosmic rarity of our current situation. The universe is currently in its stellar prime, an epoch when nuclear fusion provides abundant energy and heavy elements are widely available for planet formation. This golden age won't last forever. As star formation gradually declines and existing stars exhaust their fuel, the cosmos will enter a long twilight phase dominated by slowly cooling stellar remnants. The timescales involved in this cosmic evolution are almost incomprehensibly vast. Even the longest-lived red dwarf stars will eventually burn out, though not for trillions of years. White dwarf stars will cool to invisibility over quadrillions of years. The universe will spend most of its future existence in a cold, dark state where stellar energy sources are just fading memories of a more vibrant past. These distant futures seem almost irrelevantly remote, but they provide crucial perspective on the temporary nature of stellar energy and the preciousness of our current cosmic moment. Stellar age determination reminds us that we live during a relatively brief window when the universe is young enough to support active star formation, but old enough to have produced the heavy elements necessary for complex chemistry and life. The techniques used to measure stellar ages continue to find unexpected applications throughout astronomy. The same astroseismic methods that reveal stellar interiors are now being used to study the cores of giant planets and the structure of white dwarf stars. Gyrochronology has evolved beyond simple rotation measurements to include sophisticated models of magnetic field evolution and stellar wind interactions. Even the most exotic stellar objects yield age information when subjected to modern chronometric techniques. Neutron stars, the ultra-dense remnants of massive stellar explosions, gradually slow their rotation over millions of years as their magnetic fields drain rotational energy. By measuring these spin-down rates, astronomers can estimate how long ago these strange objects formed in supernova explosions. Pulsar timing observations have become so precise that they can detect variations in rotation period, equivalent to a clock losing 1 second over millions of years. This extraordinary precision allows astronomers to study not just pulsar ages, but also the subtle effects of gravitational waves, planetary companions, and interstellar magnetic fields on neutron star evolution. The marriage between stellar chronometry and gravitational wave astronomy has opened entirely new windows into cosmic history. When LIGO and Virgo detectors observe the merger of two neutron stars or black holes, they're witnessing the culmination of stellar evolution processes that began billions of years ago. By combining gravitational wave observations with stellar age measurements, astronomers can trace the complete life cycle of massive star systems from birth to their final cataclysmic endings. These multi-messenger observations reveal that the universe is far more dynamic and violent than previously imagined. Stellar mergers and explosions occur regularly throughout cosmic history, redistributing heavy elements and energy in ways that profoundly influence subsequent star formation and galactic evolution. Understanding these processes requires precise knowledge of stellar ages and evolutionary timescales. The field of stellar chronometry has also become essential for cosmology itself. The ages of the oldest stars provide independent constraints on the age and expansion history of the universe. When astronomers measure globular cluster ages using main sequence turn-off techniques, they're testing our fundamental understanding of cosmic chronology and the Big Bang model. These stellar age measurements must be consistent with completely independent determinations of cosmic age, based on the cosmic microwave background radiation and supernova observations. The fact that all these methods agree within their uncertainties provides powerful confirmation of our standard cosmological model and the 13.8 billion year age of the universe. Yet subtle discrepancies between different age measurement techniques continue to drive theoretical advances in both stellar physics and cosmology. Some globular clusters appear slightly older than expected based on standard stellar evolution models, suggesting either that our understanding of stellar physics is incomplete or that the early universe evolved differently than current theories predict. Resolving these apparent contradictions requires pushing stellar age measurements to even greater precision while simultaneously improving theoretical models of stellar structure and evolution. The interplay between observation and theory continues to refine our understanding of both stellar physics and cosmic history. The development of stellar chronometry has also revealed fundamental connections between astronomy and nuclear physics. The fusion processes that power stellar cores depend on nuclear reaction rates that must be measured in laboratory experiments or calculated from quantum mechanical principles. Small uncertainties in these reaction rates can translate into significant errors in stellar age determinations. Modern stellar evolution models incorporate increasingly sophisticated treatments of nuclear physics, convection, rotation, and magnetic fields. These complex simulations require some of the most powerful supercomputers available to science, generating theoretical predictions that can be compared directly with astroseismic observations and other age indicators. The precision of these theoretical models has reached the point where astronomers can detect the subtle effects of stellar rotation on evolution and age determination. Rapidly rotating stars mix their nuclear fuel more efficiently than slowly rotating ones, affecting both their lifetimes and their observable properties. Understanding these effects requires three-dimensional simulations that model the complex fluid dynamics of stellar interiors. These advances in stellar modeling have practical implications for age determination accuracy. As theoretical predictions become more sophisticated, they provide better templates for interpreting observational data. The precision of astroseismic age measurements, in particular, depends heavily on the quality of underlying stellar structure models. The quest to understand stellar aging has also driven remarkable advances in observational technology. Modern spectrographs can measure wavelength shifts equivalent to the Doppler effect from a person walking slowly across a room. Space-based photometers detect brightness variations smaller than those caused by a single grain of sand passing in front of a searchlight beam. These extreme measurement capabilities are necessary because stellar age indicators are often incredibly subtle. The frequency differences between young and old stellar oscillations amount to just a few microhertz. Chemical abundance variations that indicate different formation epochs may differ by only a few %. Rotation period changes over billions of years require detecting timing variations of just a few minutes, yet these tiny signals carry profound information about cosmic history and stellar evolution. Each measurement adds another data point to our understanding of how stars age and die, how galaxies evolve over cosmic time, and how the universe has changed since the Big Bang. The cumulative effect of thousands of precise stellar age measurements is a comprehensive picture of cosmic evolution that spans nearly 14 billion years. The applications of stellar chronometry continue to expand into new areas of astronomy and astrophysics. Planetary scientists use stellar ages to understand how planetary systems evolve and when conditions might become favorable for life. Galactic archaeologists trace the formation history of the Milky Way through the ages and chemical compositions of different stellar populations. Even the search for dark matter and modified theories of gravity benefits from precise stellar age measurements. Dark matter interactions could potentially affect stellar evolution in subtle ways that might be detectable through high-precision chronometry. Alternative theories of gravity might predict different relationships between stellar mass, age, and evolutionary timescales than standard general relativity. The future of stellar age determination promises even more remarkable discoveries. Next-generation space missions will extend astroseismic studies to fainter stars and more distant galactic regions. Extremely large ground-based telescopes will enable detailed spectroscopic studies of individual stars in nearby galaxies. Machine learning algorithms will extract age information from subtle patterns in stellar data that human researchers might never recognize. These technological advances will transform our understanding of cosmic evolution by providing precise age measurements for millions of stars across different galactic environments and cosmic epochs. The resulting database will reveal how star formation has proceeded throughout cosmic history and how different environments affect stellar evolution. Perhaps most exciting are the prospects for studying stellar populations in the early universe using next-generation space telescopes. The James Webb Space Telescope can already detect individual red giant stars in galaxies billions of light-years away. Future missions may be able to measure stellar ages in such distant systems, providing direct observational contact with cosmic epochs when star formation proceeded under completely different conditions than we observe today. The precision of modern stellar chronometry has reached levels that seemed impossible just decades ago. What began as crude estimates based on simple stellar models has evolved into a sophisticated science capable of dating individual stars to within a few % of their actual ages. These measurements provide essential context for understanding everything from planet formation to galactic evolution to the search for extraterrestrial life. The story of stellar age determination exemplifies the power of scientific methodology applied to cosmic mysteries. Through patient observation, theoretical insight, and technological innovation, astronomers have learned to extract temporal information from the faintest signals in starlight. They have transformed the apparently eternal stars into cosmic chronometers that reveal the deep history and ultimate future of the universe itself. In learning to read time in the language of starlight, humanity has gained the ability to trace our cosmic ancestry through generations of stellar death and rebirth, stretching back to the universe's earliest epochs. We are made of elements forged in stellar cores billions of years ago, and stellar chronometry allows us to read the timestamps of our cosmic heritage written in the very atoms of our existence. The quest to understand stellar aging connects us to the deepest questions about our place in the cosmos. By measuring when stars formed, how they evolve, and what fate awaits them, astronomers have revealed the temporary nature of stellar energy sources and the preciousness of our current cosmic moment. We live during a brief golden age when stars burn brightly and conditions exist for the complex chemistry that enables life. Every measurement of stellar age adds another piece to the vast puzzle of cosmic evolution. Each technique, from main sequence turn-off dating to astroseismology to nucleocosmochronology, provides a different window into the processes that govern stellar birth, evolution, and death. Together, these methods have given us the ability to read the complete biography of the universe written in starlight. The precision of these measurements continues to improve with each advancing year, driven by better telescopes, more sophisticated instruments, and deeper theoretical understanding. What once seemed impossible, determining the age of distant stars to within a few % accuracy, has become routine for modern astronomy. The future promises even greater precision and the extension of these techniques to ever more challenging stellar populations. Through the patient work of stellar astronomers across generations, we have learned that the apparently unchanging stars are actually dynamic, evolving objects that carry detailed information about cosmic history. Every photon of starlight encodes data about stellar age, composition, and evolutionary state. Every measurement reveals new details about how the cosmos has changed over its 13.8 billion year history. The techniques pioneered for stellar age determination have found applications throughout astronomy, from studying exoplanets to understanding galaxy formation to testing fundamental physics. What started as a quest to measure stellar ages has become a comprehensive framework for understanding cosmic evolution at all scales. In learning to age the stars, we have gained the keys to unlocking the temporal secrets of the universe itself. Secrets of the universe itself. The precision of modern stellar chronometry has become so refined that astronomers can now detect the fingerprints of galactic cannibalism written in stellar ages themselves. When the Milky Way consumed smaller dwarf galaxies billions of years ago, It didn't just scatter their stars throughout our galactic halo. It created distinct age signatures that persist to this day, like cosmic forensic evidence of ancient violence. These stellar refugees from destroyed galaxies carry chemical and temporal markers that distinguish them from native Milky Way stars. Their ages often cluster around specific epochs when major merger events disrupted the early galaxy's structure. By mapping these age patterns across the sky, astronomers can literally reconstruct the collision history of our cosmic neighborhood, watching billion-year-old disasters play out in slow motion through stellar archaeology. The technical sophistication required for such studies defies easy comprehension. Astronomers must measure tiny variations in stellar brightness that occur over periods of minutes or hours, then extract from these signals information about nuclear processes occurring in stellar cores, hundreds of light years away. The fact that this is possible at all represents a triumph of human ingenuity over the vastness and complexity of cosmic scales. Consider the challenge of studying stellar populations in the galactic thick disk, a component of our galaxy that formed during an era of intense star formation roughly 10 billion years ago. These ancient stars preserve chemical signatures of a cosmos that was fundamentally different from today's universe. The interstellar medium from which they formed contained far fewer heavy elements, affecting everything from their internal structure to their surface properties. Dating these thick disk stars requires combining multiple chronometric techniques with extraordinary precision. Astroseismology reveals their internal structure and evolutionary state. Chemical abundance measurements provide clues about their formation environment. Kinematic data from space missions like Gaia shows how they move through the galaxy, preserving orbital signatures of the violent processes that shaped their birth region. The results paint a picture of cosmic evolution that's both more chaotic and more organized than astronomers previously imagined. Star formation in the early galaxy proceeded in discrete bursts triggered by galaxy mergers and gas accretion events. Each episode left lasting signatures in stellar ages and chemical compositions that can still be detected today, billions of years after the original events. But stellar chronometry has also revealed unexpected connections between local and cosmic evolution. The Sun's location in the galaxy isn't random. Our solar system orbits within the galactic habitable zone, a region where stellar densities are low enough to avoid disruptive encounters, but high enough to ensure sufficient heavy element abundances for planet formation. The timing of our Sun's formation, roughly 4.5 billion years ago, placed it perfectly within this cosmic sweet spot. This temporal coincidence becomes even more remarkable when viewed against the backdrop of galactic chemical evolution. Heavy elements essential for rocky planets and life reached sufficient concentrations in our galactic neighborhood only within the last few billion years. Formed too early, and there wouldn't have been enough carbon, oxygen, and silicon for Earth-like worlds. Formed too late, and increasing stellar densities might disrupt planetary systems through gravitational encounters. The precision with which stellar ages can now be measured has revealed that our cosmic timing was extraordinarily fortunate. Small shifts in when or where our solar system formed could have dramatically altered the conditions for planetary development and biological evolution. We exist during a narrow window of cosmic history when conditions are optimal for complex chemistry and stable planetary environments. These insights emerge from statistical studies of thousands of stellar ages across different galactic regions and cosmic epochs. Space missions have measured precise ages for stars throughout the Milky Way's disk, halo, and central bulge, revealing how different components of our galaxy formed and evolved over time. The patterns show that star formation has proceeded differently in various galactic environments, with profound implications for where and when habitable worlds might arise. The central bulge, for instance, underwent rapid star formation during the galaxy's earliest epochs, quickly enriching itself with heavy elements, but also creating a crowded, high radiation environment hostile to stable planetary systems. The outer disk regions formed stars more gradually, achieving heavy element abundances suitable for planet formation only within the last few billion years. These galactic-scale patterns in stellar ages have transformed our understanding of astrobiology and the search for extraterrestrial intelligence. Rather than assuming life might arise anywhere in the universe, astronomers now recognize that complex biological evolution requires specific temporal and spatial conditions that have existed only recently in cosmic history and only in particular galactic environments. The implications extend to our search strategies for potentially habitable exoplanets. Young stellar systems may lack the heavy elements necessary for rocky planet formation. Ancient systems may have already passed through disruptive evolutionary phases that rendered previously habitable worlds uninhabitable. The optimal targets for astrobiology lie within a narrow age range that balances chemical enrichment against stellar stability. Modern exoplanet surveys increasingly incorporate stellar age information into their target selection and follow-up strategies. The James Webb Space Telescope prioritizes atmospheric characterization studies of planets orbiting stars with ages similar to our Sun, recognizing that such systems provide the best prospects for detecting biosignatures or signs of technological civilizations. But stellar chronometry has also revealed the dynamic nature of habitability over cosmic time. Planetary systems evolve along with their host stars, experiencing changing radiation environments, atmospheric evolution, and orbital dynamics that can shift habitable zones and alter surface conditions over geological timescales. Understanding these long-term changes requires precise knowledge of stellar ages and evolutionary trajectories. The relationship between stellar age and planetary habitability continues to yield surprises that challenge simple assumptions about where life might exist. Some ancient red dwarf systems show evidence of prolonged habitable conditions lasting tens of billions of years, far longer than the entire history of life on Earth. Other young massive stars might create brief but intense periods of habitability before evolving into red giants that sterilize their planetary systems. These discoveries emerge from increasingly sophisticated models that combine stellar evolution with planetary atmospheric dynamics and orbital mechanics. The calculations require supercomputers capable of simulating billions of years of coupled star-planet evolution, tracking how changing stellar properties affect planetary climates and atmospheric composition over cosmic time. The precision of these models has reached the point where astronomers can predict specific evolutionary milestones for individual stellar systems. They can calculate when a star will reach maximum luminosity, when its habitable zone will begin migrating outward, and when it will eventually exhaust its nuclear fuel and begin expanding into a red giant phase. These predictions provide cosmic perspective on Earth's future habitability and the ultimate fate of life in our solar system. Our Sun will continue brightening gradually over the next billion years, eventually triggering a runaway greenhouse effect that will boil away Earth's oceans. The precision of stellar age measurements allows astronomers to refine these timelines, providing increasingly accurate estimates of how long our planet will remain habitable. Yet even these dire long-term predictions carry seeds of hope for the continuation of life. As our Sun evolves into a red giant, its expanding atmosphere will temporarily warm the outer solar system, potentially making moons like Europa and Enceladus habitable for millions of years. Advanced civilizations might eventually migrate to these temporarily habitable worlds, or develop technologies to modify stellar evolution itself. The study of stellar ages has also revealed the cosmic rarity of our current situation. We live during the universe's stellar epoch, when nuclear fusion provides abundant energy and heavy elements are widely available for complex chemistry. This golden age represents just a tiny fraction of cosmic history, a brief interval between the universe's dark beginning and its cold future. Understanding this temporal context has profound implications for the search for extraterrestrial intelligence. If technological civilizations arise only during narrow windows of cosmic history, when stellar conditions are optimal for biological evolution, then the universe may contain far fewer advanced societies than optimistic estimates suggest. We might be among the first intelligent species to emerge, or we might be among the last. These considerations have inspired new approaches to SETI research that incorporates stellar age information into search strategies. Rather than assuming advanced civilizations might exist anywhere in the universe, astronomers now focus their searches on stellar systems with ages and chemical compositions similar to our own solar system, recognizing that such environments provide the most favorable conditions for biological and technological development. The precision of modern stellar chronometry has also enabled detailed studies of stellar populations in nearby galaxies, revealing how star formation and chemical evolution proceed under different environmental conditions. The Magellanic Clouds, our galaxy's nearest neighbors, show distinct patterns of stellar ages that reflect their different formation histories and ongoing gravitational interactions with the Milky Way. These extragalactic studies provide crucial tests of stellar evolution theory and age determination techniques. By comparing stellar populations in different galactic environments, astronomers can verify that their chronometric methods work consistently across a range of metallicities, star formation rates, and dynamical conditions. The results have confirmed the fundamental principles of stellar aging, while revealing subtle environmental effects that wouldn't be detectable in studies limited to our own galaxy. Stars in low metallicity dwarf galaxies, for instance, show slightly different age-mass relationships than their Milky Way counterparts, reflecting the influence of chemical composition on stellar structure and evolution. These discoveries have driven continuous refinement of stellar evolution models and age determination techniques. Each new observation provides additional constraints on theoretical predictions, often revealing previously unknown physical processes that affect stellar aging. The interplay between observation and theory continues to advance our understanding of how stars form, evolve, and die under various cosmic conditions. The applications of stellar chronometry now extend to some of the most fundamental questions in cosmology. When astronomers measure the ages of the oldest globular clusters, they're not just studying stellar evolution. They're testing our understanding of the universe's expansion history and the formation of the first gravitationally bound structures after the Big Bang. These ancient stellar systems formed when the universe was just a few billion years old, preserving information about cosmic conditions that no longer exist anywhere in the observable cosmos. Their ages provide independent constraints on cosmological parameters like the Hubble constant and the density of dark matter, offering checks on measurements derived from completely different astronomical phenomena. The consistency between stellar age measurements and cosmological observations based on the cosmic microwave background radiation and distant supernovae provides powerful confirmation of our standard model of cosmology. Yet subtle discrepancies between different measurement techniques continue to drive theoretical advances in both stellar physics and fundamental cosmology. Some globular clusters appear slightly older than expected, based on standard cosmological models, suggesting either that stellar evolution proceeds differently than current theories predict, or that the early universe evolved along pathways not captured by simplified models. Resolving these apparent contradictions requires pushing both observational precision and theoretical sophistication to new limits. The quest for ever more precise stellar age measurements has driven remarkable advances in astronomical instrumentation and data analysis techniques. Space-based photometers now routinely achieve precision levels of a few parts per million, enabling astroseismic studies of stars thousands of light-years away. Ground-based spectrographs can measure chemical abundances to fractional percent accuracy, revealing subtle signatures of stellar birth environments and evolutionary histories. Machine learning algorithms have become essential tools for processing the flood of data generated by modern sky surveys. Neural networks trained on stellar spectra can automatically identify age-sensitive features and extract chronometric information from observations of millions of stars simultaneously. These artificial intelligence systems often discover correlations that human researchers would never notice, revealing new connections between stellar properties and evolutionary timescales. The combination of unprecedented observational precision with sophisticated computational analysis has transformed stellar chronometry from an art practiced by individual experts into an industrial-scale science capable of dating entire galactic populations. Modern surveys routinely measure ages for hundreds of thousands of stars, creating comprehensive maps of temporal structure throughout our cosmic neighborhood. These large-scale studies have revealed that the Milky Way's formation history was far more complex than previously imagined. Rather than growing smoothly through gradual gas accretion, our galaxy experienced multiple episodes of rapid assembly, punctuated by major merger events that left lasting signatures in stellar age distributions and chemical abundance patterns. The most dramatic example involves the ancient collision between our galaxy and a smaller system called Gaia Enceladus, which occurred roughly 10 billion years ago. This merger event scattered stars throughout the galactic halo while triggering intense bursts of star formation that are still detectable today through precise age measurements of surviving stellar populations. Understanding these ancient merger events requires combining stellar chronometry with sophisticated models of galactic dynamics and chemical evolution. The calculations trace how gravitational interactions redistribute stars and gas over cosmic time while following the complex processes that govern element production and mixing throughout galactic environments. The results provide detailed timelines of galactic assembly that connect local stellar properties to cosmic structure formation on the larger scales. By measuring when different stellar populations formed and how they acquired their chemical compositions, astronomers can reconstruct the complete merger tree of our galaxy and understand how it fits into the broader context of cosmic evolution. These galactic archaeology studies have revealed that most of the Milky Way's mass was assembled relatively recently in cosmic terms, with major structural components forming within the last 8 to 10 billion years. This timeline places our galaxy's formation well after the peak epoch of cosmic star formation, when the universe was roughly 3 billion years old and forming stars at rates much higher than observed today. The implications extend beyond local galactic evolution to our understanding of how galaxies form and evolve throughout cosmic history. The Milky Way appears to be fairly typical among spiral galaxies of similar mass, suggesting that the formation processes revealed through stellar chronometry operate universally across different galactic environments and cosmic epochs. Modern stellar age measurements have also uncovered unexpected diversity in how different galactic components formed and evolved. The thick disk contains stars with a wide range of ages and chemical compositions, reflecting a complex formation history involving multiple episodes of star formation and chemical enrichment. The thin disk shows more organized age gradients that trace the gradual buildup of galactic structure over the last several billion years. Even the galactic halo, once thought to be a simple collection of ancient stars left over from the galaxy's earliest formation phases, shows evidence of multiple stellar populations with different ages and origins. Some halo stars formed in situ during the galaxy's initial collapse, while others were accreted from disrupted satellite galaxies over extended periods of cosmic time. These discoveries have emerged only through the application of multiple complementary chronometric techniques to large samples of stars across different galactic regions. No single age determination method works optimally for all stellar types and evolutionary stages. But the combination of different approaches provides robust age estimates that reveal subtle patterns invisible to any individual technique. The future of stellar chronometry promises even more remarkable discoveries as observational capabilities continue to advance. Next-generation space missions will extend asteroseismic studies to fainter stars and more distant galactic regions, while ground-based, extremely large telescopes will enable detailed spectroscopic studies of individual stars in nearby galaxies. These technological advances will provide age measurements for stellar populations that formed under completely different conditions than anything observable in our local galactic environment. By studying how stellar evolution proceeds in low metallicity dwarf galaxies or high-density galactic centers, astronomers will test the universality of stellar aging processes across a wide range of cosmic environments. The precision of these future measurements will also enable studies of stellar evolution on timescales comparable to the age of the universe itself. By comparing the detailed properties of the oldest stellar populations with theoretical predictions, astronomers will gain unprecedented insights into the physical processes that govern stellar birth, evolution, and death under primordial cosmic conditions. Perhaps most exciting are the prospects for detecting and studying population 3 stars, the hypothetical first generation of stellar objects that formed from primordial hydrogen and helium in the early universe. These exotic objects, if any survive today, would provide direct observational contact with cosmic conditions that existed when the universe was emerging from its dark ages and beginning to forge the first heavy elements. The technical challenges involved in such studies push current technology to its absolute limits. Population 3 remnants would be incredibly rare and faint, requiring the most sensitive telescopes and sophisticated analysis techniques available to astronomy. Yet the potential scientific rewards justify the extraordinary effort, as such discoveries would revolutionize our understanding of the earliest phases of cosmic evolution. The quest to understand stellar aging has become one of astronomy's most successful examples of combining observational precision with theoretical sophistication to extract profound insights about cosmic history. From humble beginnings as rough estimates based on simple stellar models, stellar chronometry has evolved into a precision science capable of dating individual objects to within a few % of their actual ages. These measurements provide essential context for understanding everything from planet formation to galactic evolution to the ultimate fate of the universe itself. Every determination of stellar age adds another piece to the vast temporal puzzle of cosmic evolution, revealing how the universe has changed from its simple beginnings into the complex, chemically rich cosmos we observe today. The story of stellar chronometry exemplifies science at its most elegant and powerful, demonstrating how patient observation, theoretical insight, and technological innovation can unlock the deepest secrets of nature. Through the development of increasingly sophisticated techniques for reading time in starlight, astronomers have gained the ability to trace cosmic history across nearly 14 billion years of universal evolution. In learning to age the stars, we have discovered not just when celestial objects formed, but how they connect to the grand narrative of cosmic evolution that encompasses everything from the formation of the first atoms to the eventual emergence of life and intelligence. The precision of modern stellar age measurements has revealed that we exist during a precious and temporary epoch, when conditions are optimal for complex chemistry and biological evolution. Every photon of starlight carries temporal information about the cosmic environment in which it originated. Every measurement of stellar age provides another glimpse into the deep history of the universe and the processes that have shaped our cosmic neighborhood over billions of years. Through the patient work of stellar astronomers, we have learned to read these temporal messages, written in the language of nuclear physics and gravitational dynamics. The techniques pioneered for stellar age determination continue to find new applications throughout astronomy and astrophysics, from studying the formation of planetary systems, to understanding the evolution of galaxies, to testing fundamental theories of physics and cosmology. What began as a quest to measure when stars formed has become a comprehensive framework for understanding temporal relationships throughout the cosmos. The precision of these measurements will continue to improve as technology advances and theoretical understanding deepens. Future generations of astronomers will push stellar chronometry to even greater accuracy, revealing ever more subtle details about how the universe has evolved over cosmic time and what fate awaits stellar populations in the distant future. Through stellar age determination, we have gained not just scientific knowledge, but cosmic perspective on our place in the universal story. We are made of elements forged in stellar cores billions of years ago, and stellar chronometry allows us to trace the complete timeline of our cosmic ancestry from the Big Bang, through successive generations of stellar death and rebirth, to the formation of our solar system and the emergence of life on Earth. The quest to understand stellar aging connects us to the deepest questions about time, change, and permanence in the cosmos. By learning to read the ages of distant stars, we have discovered that even the most stable and long-lived objects in the universe are temporary, evolving entities that carry within themselves the history of cosmic evolution and the seeds of future change. In the end, stellar chronometry reminds us that we live during a brief and remarkable moment in cosmic history, when stars burn brightly and conditions exist for the complex chemistry that enables life and consciousness. The precision with which we can now measure stellar ages provides both humbling perspective on our cosmic insignificance and inspiring evidence of our species' ability to comprehend the deepest workings of the universe itself. The precision of stellar chronometry has reached levels that would have seemed like pure fantasy to astronomers working just a generation ago. Modern techniques can distinguish between stars that formed 8 billion years ago versus 8.1 billion years ago, differences that amount to just over 1% of their total lifetimes. This extraordinary accuracy emerges from the marriage of space-based observations with computational models that simulate stellar evolution in unprecedented detail. Consider what this means in practical terms. When astronomers measure the age of a star located thousands of light years away, they're essentially performing cosmic forensics on nuclear processes that occurred before our solar system existed. They're reading the subtle signatures of hydrogen fusion rates, helium-burning phases, and convective mixing patterns that played out over timescales that dwarf all of human history. The fact that such measurements are possible at all represents one of the most remarkable achievements in the history of science. The technical sophistication required for these studies pushes every aspect of astronomical observation to its limits. Space telescopes must maintain pointing stability to within thousandths of an arcsecond, while measuring brightness variations smaller than those caused by atmospheric turbulence on Earth. Spectrographs must resolve wavelength differences equivalent to distinguishing between colors that differ by less than the width of an atomic nucleus. Computer models must simulate the complex three-dimensional dynamics of stellar interiors across billions of years of evolution. Yet these extreme requirements yield insights that transform our understanding of cosmic history in ways that continue to surprise even experienced researchers. When astronomers map the age structure of stellar populations across the galaxy, they're not just creating a census of when stars formed, they're revealing the hidden architecture of cosmic time itself, the temporal scaffolding that underlies everything from planet formation to the chemical evolution of the universe. The patterns that emerge from these studies paint a picture of cosmic evolution that's both more organized and more chaotic than anyone anticipated. Star formation doesn't proceed smoothly and continuously. Instead, it occurs in discrete bursts triggered by galactic collisions, gas accretion events, and the complex feedback loops between stellar death and birth. Each episode leaves distinctive signatures in stellar ages and chemical compositions that persist for billions of years. These temporal patterns become particularly striking when astronomers compare stellar populations in different galactic environments. The central bulge of our galaxy underwent rapid star formation during the universe's first few billion years, quickly enriching itself with heavy elements but creating a crowded, high-energy environment where planetary systems might struggle to form and survive. The outer disk regions evolved more gradually, reaching heavy element concentrations suitable for rocky planet formation only within the last few billion years. The implications for astrobiology are profound and unsettling. If complex life requires both chemical enrichment and stellar stability, then vast regions of our galaxy may have been uninhabitable for most of cosmic history. We might be among the first generations of intelligent beings to emerge, products of a cosmic convergence that aligned stellar ages, chemical abundances, and galactic dynamics in just the right way to enable biological complexity. This temporal perspective on habitability has revolutionized how astronomers approach the search for extraterrestrial intelligence. Rather than assuming life might arise anywhere in the universe, researchers now recognize that biological evolution requires specific chronological windows that have opened only recently in cosmic terms. The optimal conditions for complex chemistry may have existed for mere billions of years out of the universe's 13.8 billion year history. Modern CT searches increasingly incorporate stellar age information into their target selection strategies. The most promising candidates are stars with ages similar to our Sun, old enough to have developed stable planetary systems, but young enough to avoid the disruptive evolutionary phases that will eventually render solar-type stars uninhabitable. This temporal Goldilocks zone represents a narrow slice of cosmic time when conditions favor the emergence and persistence of technological civilizations. But stellar chronometry has also revealed the dynamic nature of habitability over geological timescales. Planetary systems don't simply exist in habitable or uninhabitable states. They evolve along complex trajectories determined by their host star's age and evolutionary status. Young systems may lack the chemical ingredients necessary for life. Ancient systems may have passed through phases where stellar evolution disrupted previously habitable conditions. Understanding these temporal transitions requires combining stellar age measurements with sophisticated models of planetary atmospheric evolution and orbital dynamics. The calculations trace how changing stellar luminosity affects surface temperatures, atmospheric chemistry, and the stability of liquid water over billions of years. The results reveal that habitability is not a permanent condition, but a temporary state that can begin and end multiple times during a planetary system's lifetime. These insights have particular relevance for Earth's future and the long-term survival of terrestrial life. Our Sun's gradual brightening will eventually trigger a runaway greenhouse effect that boils away the oceans. But this catastrophic transition won't occur for roughly another billion years. The precision of stellar age measurements allows astronomers to refine these predictions, providing increasingly accurate timelines for our planet's habitability. Yet even these dire projections carry unexpected implications for the continuation of life. As our Sun evolves toward its red giant phase, its expanding luminosity will temporarily warm the outer solar system, potentially making moons like Europa and Enceladus habitable for millions of years. Advanced civilizations might eventually migrate to these temporarily habitable worlds or develop technologies to modify stellar evolution itself. The study of stellar ages has also revealed connections between local and cosmic evolution that illuminate our place in the universal story. The Sun's formation roughly 4.5 billion years ago occurred during a period when our galactic neighborhood had just reached the chemical enrichment levels necessary for rocky planet formation. Earlier epochs lacked sufficient heavy elements. Later periods might involve stellar densities too high for stable planetary evolution. This temporal coincidence suggests that our existence depends not just on the right spatial location within the galaxy, but on precise timing within cosmic history. We live during a narrow window when conditions throughout our galactic region became optimal for complex chemistry and biological evolution. Small shifts in when our solar system formed could have dramatically altered the prospects for planetary development and the emergence of life. Understanding this cosmic timing requires measuring stellar ages across vast regions of space and time. Modern surveys have determined precise ages for hundreds of thousands of stars throughout different galactic components, revealing how star formation has proceeded over nearly the entire history of our galaxy. The patterns show that heavy element production and distribution followed complex pathways that created habitable conditions only within specific temporal and spatial windows. The precision of these large-scale age measurements has uncovered galactic evolution processes that weren't apparent in smaller studies. The Milky Way's formation history emerges as a complex narrative involving multiple merger events, gas accretion episodes, and periods of enhanced star formation that shape the chemical and temporal structure of different galactic components. Each phase left distinctive signatures in stellar age distributions that can still be detected today. Perhaps the most remarkable discovery involves the identification of stellar populations that formed in completely different galactic environments than anything observable today. Some ancient halo stars show chemical abundance patterns, suggesting they originated in small dwarf galaxies that were later consumed by the growing Milky Way. Their ages cluster around epochs when major merger events disrupted the early galaxy's structure and triggered intense bursts of star formation. These stellar refugees from destroyed galaxies carry temporal and chemical fingerprints that allow astronomers to reconstruct collision events that occurred billions of years ago. By measuring their ages and orbital motions, researchers can literally watch ancient galactic catastrophes playing out in slow motion through the archaeological record preserved in stellar populations. The techniques required for such studies combine multiple cutting-edge approaches to stellar chronometry. Asteroseismology reveals internal structures and evolutionary states. Chemical abundance measurements provide clues about formation environments. Astrometric data from space missions shows how stars move through the galaxy, preserving kinematic signatures of the violent processes that shape their birth regions. When all these methods agree, astronomers gain extraordinary confidence in their age determinations. When they disagree, it often signals that something fascinating and unexpected is occurring that standard models don't predict. These discrepancies have led to discoveries of exotic stellar populations, previously unknown evolutionary pathways, and subtle environmental effects that influence how stars age under different cosmic conditions. The relationship between stellar age and galactic chemical evolution has become one of the most active areas of modern astronomical research. Each generation of stars changes the composition of interstellar gas through stellar winds and explosive deaths. These compositional changes affect the properties of subsequently forming stars, creating feedback loops that influence galactic evolution over cosmic timescales. Tracing these chemical pathways requires measuring both ages and abundances for large samples of stars across different galactic regions. The results reveal that element production and distribution proceeded differently in various environments, with profound implications for when and where planetary systems suitable for life could begin forming. The central regions of our galaxy, for instance, underwent rapid chemical enrichment during the first few billion years of cosmic history. Heavy elements reached concentrations suitable for planet formation much earlier than in the outer disk regions. However, the crowded, high-energy environment of the galactic center might have prevented stable planetary systems from surviving long enough for biological evolution to occur. The outer disk regions evolved more slowly, reaching planet-forming metallicities only within the last few billion years. But these regions also provided calmer environments where planetary systems could develop and persist over the extended timescales required for complex chemistry and biological evolution. The optimal combination of chemical enrichment and environmental stability occurred only in narrow spatial and temporal windows. Understanding these galactic habitability patterns requires combining stellar chronometry with models of planetary formation and evolution. The calculations must account for how stellar ages affect planetary atmospheric development, how galactic environments influence planetary system stability, and how chemical evolution determines the availability of elements essential for rocky planets and biological chemistry. The precision of modern stellar age measurements has enabled studies that trace these relationships across billions of years of galactic evolution. By mapping how habitability conditions have changed throughout different galactic regions and cosmic epochs, astronomers are creating the first comprehensive models of where and when life might have emerged throughout our cosmic neighborhood. These models suggest that the conditions favorable for complex life have existed for only a small fraction of cosmic history and only in specific galactic regions. The universe may contain far fewer habitable worlds than optimistic estimates suggest, not because planets are rare, but because the temporal and spatial windows for habitability are much narrower than previously imagined. The implications extend beyond academic speculation to practical considerations for the search for extraterrestrial intelligence. If technological civilizations can only arise during brief periods when stellar, chemical, and galactic conditions align appropriately, then the universe might contain fewer advanced societies than many researchers hope. We might be among the earliest intelligent species to emerge from this cosmic convergence. Alternatively, if life proves more adaptable than current models predict, then the universe might harbor forms of intelligence that arose under completely different conditions than those that enabled biological evolution on Earth. Understanding the temporal constraints on habitability provides essential context for interpreting the results of searches for extraterrestrial life and intelligence. The quest to measure stellar ages has also driven remarkable advances in our understanding of stellar physics itself. Each new chronometric technique reveals previously unknown aspects of how stars form, evolve, and die. Asteroseismology has uncovered complex internal dynamics that weren't predicted by simplified stellar models. Gyrochronology has revealed the intricate relationships between rotation, magnetic fields, and stellar winds that govern how stars lose angular momentum over cosmic time. These discoveries continue to refine theoretical models of stellar evolution and improve the accuracy of age determinations. As models become more sophisticated, they provide better templates for interpreting observational data and extracting chronometric information from subtle stellar signals. The precision of astroseismic age measurements, in particular, depends heavily on the quality of underlying stellar structure calculations. The interplay between observation and theory has led to continuous improvements in both stellar models and measurement techniques. Each new discovery of unexpected stellar behavior drives theoretical advances that enhance our understanding of stellar physics. Each improvement in theoretical models enables more precise interpretation of observational data and more accurate age determinations. This feedback loop between observation and theory exemplifies science at its most productive, where empirical discoveries and theoretical insights reinforce each other to advance understanding of complex natural phenomena. The field of stellar chronometry has benefited enormously from this synergy, evolving from crude estimates based on simple models to precision measurements that rival the accuracy of geological dating techniques. The applications of stellar age determination continue to expand into new areas of astronomy and astrophysics. Planetary scientists use stellar chronometry to understand how planetary systems evolve and when conditions become favorable for biological development. Galactic archaeologists trace the formation history of our galaxy through the temporal signatures preserved in different stellar populations. Even fundamental physics benefits from precise stellar age measurements. The nuclear fusion processes that power stellar cores depend on fundamental constants like the strong nuclear force and electromagnetic coupling. Detailed studies of stellar evolution provide tests of whether these constants have remained unchanged over cosmic history, offering unique probes of physics under extreme conditions that can't be replicated in terrestrial laboratories. The precision of modern stellar chronometry has reached levels where astronomers can detect subtle variations in nuclear burning rates that might indicate changes in fundamental physics over cosmic time. While no such variations have been confirmed, the possibility keeps theorists interested in pushing stellar age measurements to ever greater accuracy and testing the consistency of physical laws across vast, temporal, and spatial scales. The future of stellar chronometry promises even more remarkable discoveries as observational capabilities continue advancing. Next-generation space telescopes will extend asteroseismic studies to fainter stars and more distant galactic regions. Extremely large ground-based telescopes will enable detailed spectroscopic analysis of individual stars in nearby galaxies, testing whether stellar evolution proceeds identically under different cosmic conditions. These technological advances will provide age measurements for stellar populations that formed under environmental conditions completely unlike anything observable in our local galactic region. By studying how stellar aging proceeds in low metallicity dwarf galaxies or high-density galactic centers, astronomers will test the universality of stellar evolution processes across diverse cosmic environments. Perhaps most exciting are the prospects for detecting and studying the oldest stellar populations in the universe. These ancient objects formed when cosmic conditions were fundamentally different from today, when the universe contained almost no elements heavier than hydrogen and helium. Finding and characterizing such stars would provide direct observational contact with the earliest epochs of cosmic evolution. The technical challenges involved in studying these primordial stellar populations push current astronomical capabilities to their absolute limits. The oldest stars are incredibly rare and faint, requiring the most sensitive telescopes and sophisticated analysis techniques available to modern astronomy. Yet the scientific rewards justify the extraordinary effort required for such studies. Discovery of genuine population 3 remnants would revolutionize our understanding of the earliest phases of cosmic history, providing direct evidence of conditions that existed when the universe was emerging from its dark ages. These objects would carry chemical and temporal signatures of the first stellar generation, offering unprecedented insights into how the universe transitioned from its simple post-Big Bang state to the complex chemically enriched cosmos we observe today. The quest to understand stellar aging has become one of astronomy's most successful examples of how patient observation, theoretical sophistication, and technological innovation can unlock profound insights about cosmic history. From humble beginnings as rough estimates based on simple stellar models, stellar chronometry has evolved into a precision science that rivals any measurement technique in the physical sciences. These advances have transformed our understanding of cosmic evolution by providing the temporal framework necessary to trace how the universe has changed over nearly 14 billion years of history. Every measurement of stellar age adds another data point to this cosmic timeline, revealing connections between local phenomena and universal processes that operate on the grandest scales imaginable. The story of stellar chronometry illustrates how seemingly impossible scientific challenges yield to human persistence and ingenuity. What once appeared hopeless, determining the ages of distant stars that barely change over billions of years, has become routine through the development of increasingly sophisticated observational and theoretical techniques. Through the patient work of stellar astronomers across multiple generations, we have learned to read time itself in the language of starlight. Every photon carries temporal information about the cosmic environment in which it originated. Every measurement reveals new details about how stars form, evolve, and die under the changing conditions that have characterized cosmic evolution since the Big Bang. The precision of modern stellar age determinations has revealed that we exist during a remarkable and temporary epoch in cosmic history. The conditions that enable complex chemistry and biological evolution have existed for only a small fraction of universal history and may persist for only a limited time into the cosmic future. We are witnesses to and products of a brief golden age when stars burn brightly and the universe supports the intricate processes that give rise to planets, life, and consciousness. In learning to measure the ages of distant stars, we have gained not just scientific knowledge, but cosmic perspective on our place in the universal story. The techniques that reveal when stars formed also illuminate the temporal relationships that connect our existence to the deep history of cosmic evolution. We are made of elements forged in stellar cores billions of years ago, and stellar chronometry allows us to trace the complete timeline of our cosmic ancestry. The quest to understand stellar aging connects us to the most fundamental questions about time, change, and permanence in the cosmos. Through the development of increasingly precise chronometric techniques, astronomers have discovered that even the most stable objects in the universe are temporary, evolving entities that carry within themselves both the history of cosmic evolution and the seeds of future change. Every measurement of stellar age provides another glimpse into the deep workings of the universe, revealing how nuclear physics, gravitational dynamics, and cosmic chemistry have conspired over vast scales of space and time to create the conditions that enable our existence. In reading the ages written in starlight, we discover not just when celestial objects formed, but how they connect to the grand narrative of cosmic evolution that encompasses everything from the first moments after the Big Bang to the eventual emergence of life and intelligence. The precision of stellar chronometry will continue improving as technology advances and theoretical understanding deepens. Future generations of astronomers will push these measurements to even greater accuracy, revealing ever more subtle details about how the universe has evolved and what fate awaits stellar populations in the distant cosmic future. Through stellar age determination, we have learned to read the temporal signatures written in the very fabric of cosmic history itself. The intersection of stellar chronometry and cosmology has revealed one of the most profound confirmations of our understanding of universal history. When astronomers measure the ages of the oldest globular clusters scattered throughout our galactic halo, they're not just dating ancient stellar populations. They're conducting independent tests of the Big Bang model itself, using stellar nuclear physics to verify timescales derived from completely different cosmic phenomena. These ancient stellar systems formed when the universe was still young, chaotic, and fundamentally different from the organized cosmos we observe today. Their ages, determined through painstaking main sequence turn-off analysis and asteroseismic studies, consistently point to formation epochs between 11 and 13 billion years ago. This timeline aligns remarkably well with cosmic age estimates, based on the expansion rate of the universe and the temperature fluctuations preserved in the cosmic microwave background radiation. The consistency between these completely independent measurements provides extraordinary validation of our cosmological models. if stellar evolution theory were fundamentally flawed, or if our understanding of cosmic expansion were incorrect. These different approaches would yield contradictory results. Instead, they converge on a coherent picture of universal history that spans from the first moments after the Big Bang to the present day. Yet this convergence required decades of refinement in both stellar physics and cosmological theory. Early measurements of globular cluster ages occasionally suggested these ancient systems were older than the universe itself, a cosmic impossibility that sent theorists scrambling to resolve the apparent contradiction. The resolution came through more sophisticated modeling of stellar evolution, better measurements of cosmic expansion rates, and deeper understanding of how the first stellar populations formed under primordial conditions. These apparent paradoxes weren't failures of scientific methodology. They were opportunities for discovery, revealing subtle effects that simpler models had overlooked. The process of reconciling stellar ages with cosmic chronology led to breakthroughs in understanding everything from nuclear reaction rates in stellar cores to the influence of dark energy on universal expansion. Modern measurements have eliminated these early discrepancies, but they've also revealed new puzzles that continue to drive theoretical advances. Some of the oldest stars show chemical abundance patterns that don't quite match predictions for primordial nucleosynthesis, suggesting that the early universe was more complex than simplified models assume. These anomalies provide clues to physical processes that operated during cosmic epochs we can study only through their fossil signatures preserved in ancient stellar populations. The technical precision required for these studies pushes astronomical observation to its absolute limits. Measuring the age of a globular cluster demands determining the exact temperature and luminosity at which main sequence turnoff occurs, then comparing this observational data with theoretical isochrones that model stellar evolution over billions of years. The measurements must account for distance uncertainties, interstellar extinction, and subtle variations in chemical composition that affect stellar properties. Each globular cluster becomes a cosmic laboratory where astronomers can test their understanding of stellar physics under extreme conditions. These systems contain hundreds of thousands of stars packed into regions just a few tens of light years across, creating gravitational environments unlike anything found elsewhere in the galaxy. The intense stellar interactions can alter evolutionary timescales through mechanisms like stellar collisions, mass transfer between close companions, and the complex dynamics of multiple star systems. Understanding these environmental effects requires sophisticated computational models that simulate the evolution of entire stellar populations over cosmic time. The calculations must account for gravitational interactions between thousands of individual stars, while simultaneously modeling the nuclear physics that governs stellar aging. The computational demands are so extreme that complete cluster evolution simulations require months of processing time on the world's most powerful supercomputers. These detailed simulations have revealed that globular clusters are far more dynamic and complex than early astronomers realized. Rather than simple collections of coeval stars aging peacefully over cosmic time, these systems undergo dramatic internal evolution driven by gravitational interactions, stellar collisions, and the gradual loss of lower mass stars to the galactic tidal field. Some of the exotic stellar objects found in globular clusters exist nowhere else in the galaxy. Blue straggler stars appear younger and more massive than they should be, having gained mass through collisions or interactions with companion stars. Millisecond pulsars spin hundreds of times per second, having been spun up through accretion from companion stars in close binary systems. X-ray sources mark the locations where compact stellar remnants are actively consuming material from nearby stellar companions. Dating these exotic objects requires specialized chronometric techniques that account for their unusual evolutionary histories. Traditional main sequence turn-off dating fails for stars that have gained mass through interactions or collisions. Gyrochronology becomes complicated when stellar rotation has been altered by tidal interactions or mass transfer events. Even asteroseismology can yield misleading results for stars whose internal structures have been modified by external processes. Yet these challenges also provide unique opportunities to test stellar evolution theory under extreme conditions. Globular clusters serve as natural experiments where astronomers can study how stellar aging proceeds in high-density environments, unlike anything found in the galactic disk. The results reveal that stellar evolution is more complex and varied than models based on isolated field stars would suggest. The diversity of stellar populations within individual globular clusters has emerged as one of the most surprising discoveries of modern stellar chronometry. Rather than containing single generations of coeval stars, many clusters show evidence of multiple formation episodes spanning hundreds of millions of years. These complex formation histories challenge simple models of cluster origin and evolution. Understanding when and how these multiple populations formed requires combining stellar age measurements with detailed chemical abundance analysis. Different stellar generations often show distinct abundance patterns reflecting the changing composition of cluster gas over time. The oldest stars formed from relatively pristine material, while younger populations show evidence of enrichment by the nuclear products of earlier stellar generations. These chemical evolution patterns provide unique insights into how the first stellar populations processed primordial gas into the heavy elements that would eventually enable planet formation throughout the universe. Globular clusters preserve fossil records of nucleosynthesis processes that operated when the cosmos was young and metal-poor, offering direct observational contact with cosmic conditions that no longer exist anywhere in the observable universe. The implications extend far beyond cluster evolution to our understanding of how galaxies formed and evolved during the universe's first few billion years. Globular clusters appear to be survivors from an early epoch when star formation proceeded under completely different conditions than we observe in the modern universe. Their chemical and temporal signatures provide clues to how the first galaxies assembled from smaller building blocks in the cosmic dark ages. Recent studies have revealed that globular clusters in different parts of our galaxy show systematic age differences that trace the assembly history of the Milky Way itself. Clusters in the inner halo tend to be older than those in the outer regions, suggesting that galaxy formation proceeded from the inside out over extended periods of cosmic time. Some clusters show kinematic signatures indicating they were accreted from smaller satellite galaxies that were later disrupted by tidal forces. These discoveries have emerged from combining precise age measurements with the extraordinary astrometric data provided by space missions like Gaia. By measuring the three-dimensional motions of globular clusters throughout the galactic halo, astronomers can trace their orbital histories backward through billions of years of galactic evolution. The results reveal a complex formation scenario where our galaxy grew through the gradual accretion and disruption of numerous smaller systems. The precision of modern cluster age measurements has become sufficient to detect the gravitational influence of dark matter on stellar evolution timescales. Dark matter, halos, affect the formation and evolution of stellar systems in subtle ways that might be detectable through high-precision chronometry. While no such effects have been confirmed, the possibility drives continued efforts to push stellar age measurements to ever greater accuracy. The relationship between cluster ages and their chemical compositions continues to yield insights into the earliest phases of cosmic chemical evolution. The most metal-poor clusters formed when the universe contained almost no elements heavier than hydrogen and helium, providing direct observational access to conditions that existed shortly after the first stars began forging heavy elements in their nuclear furnaces. These primordial clusters preserve information about nucleosynthesis processes that operated under extreme conditions, unlike anything found in the modern universe. Their chemical abundance patterns reflect the products of massive stars that lived and died when cosmic metallicity was orders of magnitude lower than today. Understanding these early enrichment processes requires combining stellar chronometry with detailed models of supernova nucleosynthesis and the chemical evolution of the early universe. The search for the oldest stellar populations continues to push the boundaries of observational astronomy and theoretical modeling. Each new discovery of an ancient cluster or individual star provides additional constraints on models of cosmic evolution and stellar nucleosynthesis. The cumulative effect of thousands of precise age measurements is a comprehensive picture of how the universe has evolved from its simple post-Big Bang state to the complex, chemically enriched cosmos we observe today. The precision of stellar chronometry has also enabled detailed studies of how cosmic expansion affects stellar evolution over vast timescales. The density and temperature of the early universe were significantly different from current values, potentially affecting nuclear reaction rates and stellar structure in ways that might be detectable through sufficiently precise age measurements. While such effects are likely to be extremely small, they represent fundamental tests of physics under conditions that can't be replicated in terrestrial laboratories. Modern globular cluster studies have revealed unexpected connections between stellar aging and the large-scale structure of the universe. Clusters that formed in different cosmic environments show subtle but systematic differences in their stellar populations and chemical evolution patterns. These variations provide clues to how the cosmic web of dark matter and ordinary matter influenced star formation during the universe's earliest epochs. The technical challenges involved in measuring globular cluster ages continue to drive advances in both observational techniques and theoretical modeling. Space-based telescopes provide the photometric precision necessary to detect subtle variations in stellar brightness that reveal evolutionary states. Ground-based spectrographs measure chemical abundances with accuracy sufficient to distinguish between different nucleosynthesis scenarios. Computational models simulate cluster evolution with unprecedented detail and sophistication. Each improvement in measurement precision reveals new subtleties in cluster evolution and stellar aging processes. What once seemed like simple collections of ancient stars have revealed themselves to be complex, dynamic systems that preserve detailed records of cosmic evolution spanning billions of years. The story written in their stellar populations connects local galactic archaeology to the grandest questions about cosmic origins and the fundamental nature of the universe itself. The quest to understand stellar aging through globular cluster studies exemplifies astronomy at its most ambitious and successful. By combining patient observation with sophisticated theoretical modeling, astronomers have transformed these ancient stellar systems into cosmic laboratories that reveal the deep history of the universe. Every measurement adds another piece to the vast temporal puzzle of cosmic evolution. Through the study of globular clusters, we have learned that the universe's history is written not just in the cosmic microwave background or distant galaxies, but in the nuclear furnaces of ancient stars that continue burning in our cosmic neighborhood. These stellar time capsules preserve information about epochs when the cosmos was young, and the conditions that would eventually give rise to galaxies, planets, and life were just beginning to emerge from primordial simplicity. The precision of modern stellar chronometry has revealed that we exist during a remarkable moment in cosmic history, when these ancient witnesses to universal evolution remain observable and accessible to detailed study. In learning to read the ages written in their starlight, we have gained unprecedented insights into how the universe has changed over nearly its entire history and what processes shaped the cosmic environment that enabled our own existence. The precision of these ancient stellar chronometers has become so extraordinary that astronomers can now detect the signatures of cosmic events that shaped our universe billions of years before Earth even existed. When they analyze the light from metal-poor stars scattered throughout our galactic halo, they're essentially reading cosmic archaeology written in nuclear physics. These stellar relics carry within their atmospheres the chemical fingerprints of the very first supernovae, the massive stellar explosions that seeded space with elements heavier than hydrogen and helium. What makes this discovery so remarkable is the technical virtuosity required to extract such information. Imagine trying to determine the vintage of a wine by analyzing a single molecule that's been diluted in an ocean. That's essentially what astronomers accomplish when they detect traces of europium or strontium in stars whose light has traveled for thousands of years to reach our telescopes. These measurements require spectrographs so sensitive they can distinguish between atomic transitions that differ by fractions of an angstrom. The story these ancient stars tell is both humbling and extraordinary. Some formed when the Milky Way was still a chaotic collection of smaller galaxies violently merging together. Others preserve evidence of stellar populations that no longer exist anywhere in the observable universe. Each spectrum becomes a time machine, revealing cosmic conditions that prevailed when the universe was a fundamentally different place than the organized, chemically rich cosmos we observe today. But perhaps the most mind-bending aspect of stellar chronometry involves its ability to predict cosmic futures with the same precision it reveals cosmic pasts. By measuring the current ages and evolutionary states of stars throughout our galaxy, astronomers can calculate exactly when different stellar populations will exhaust their nuclear fuel and begin their final transformations. The models paint detailed pictures of how our cosmic neighborhood will evolve over the next 100 billion years. Consider what this means for the ultimate fate of stellar energy in the universe. We live during what cosmologists call the stelliferous era, when nuclear fusion provides abundant light and heat throughout the cosmos. But this golden age won't last forever. Massive stars will exhaust their fuel and explode within millions of years. Sun-like stars will burn steadily for billions of years before swelling into red giants and eventually cooling into white dwarfs. Even the smallest red dwarf stars will eventually run out of nuclear fuel, though not for trillions of years. The precision of stellar age measurements allows astronomers to create detailed timelines for this cosmic twilight. They can calculate when the last red dwarf will finally exhaust its hydrogen fuel, marking the end of the stelliferous era and the beginning of a dark age dominated by slowly cooling stellar remnants. These predictions stretch across timescales so vast, they make the entire history of life on Earth seem like a fleeting moment. Yet within these cosmic timelines lie hidden opportunities for the continuation of complex processes. As our sun evolves toward its red giant phase, billions of years from now, its expanding luminosity will temporarily warm the outer solar system, potentially making moons like Europa and Titan habitable for extended periods. Advanced civilizations might learn to harness the energy released during stellar evolution itself, finding ways to extract useful work from the very processes that mark the aging of stars. The relationship between stellar chronometry and the search for life has become increasingly sophisticated, as astronomers recognize that biological evolution requires specific temporal windows when stellar conditions remain stable. Young stars unleash powerful radiation and magnetic activity that can strip away planetary atmospheres before complex chemistry has time to develop. Ancient stars may have already passed through disruptive evolutionary phases that render previously habitable worlds uninhabitable. Finding the optimal balance requires understanding not just stellar ages, but the complete evolutionary trajectories that determine how stellar properties change over cosmic time. A planet orbiting a star that's currently in its stable main sequence phase might seem habitable today, But if that star is approaching the end of its hydrogen-burning lifetime, the habitability window could close within just a few million years. And that brings us to the end of our cosmic journey through the remarkable science of stellar chronometry. From the elegant simplicity of main sequence turn-off, dating to the mind-bending precision of asteroseismology, we've explored how astronomers transformed an seemingly impossible challenge into one of science's greatest triumphs. These techniques don't just tell us when stars formed. They've given us the ability to read the entire biography of the universe written in starlight itself. Every measurement adds another piece to the vast temporal puzzle of cosmic evolution, revealing how we're all connected to stellar generations that lived and died billions of years before our solar system even existed. Thanks for joining me on this exploration of cosmic time. Let me know in the comments which stellar age determination technique fascinated you most. And I'll see you in the next video where we'll dive into another mind-blowing aspect of our universe.